So welcome back, everyone. So today we're going to talk about the graphs and some of its applications and some of their algorithms of the graph, which is going to be the last topic of our course, and that's also chapter 28 of the book. So the graph has a lot of applications. Mainly is using for modeling purposes. So here in this example, we have the graph of the different countries and how they connected to each other. Maybe that's for the airlines, or that's for the telecommunications or networks or whatever. So this is a model of some sort of a relations, or maybe like even the roads from one state to another. So as you can see, we'll put some indexes for each of the states that we have, and we show them as some sort of a dots. So and then we connect them whenever they're really connected to each other. If there is a road from Seattle to Denver, then we connect these two states together. If there's no direct road, then we're not connecting. As you can see, Seattle is not connected directly to the Boston, but you can go to Chicago, and then from Chicago you can go to Boston or New York, right? So only have a direct connection or direct edge if, for example, there is a route there. So there's a road basically there, right? So basically, these are the indexes for sometimes it's easier to use index instead of the entire string, right? So it's like in language such as Java, so string is an object by itself, right? So the objects are going to be more expensive to be stored. So you can use instead of the entire string object, you can use the integer primitive type object, which is going to store a lot less memory, right? So the graphs are basically mainly used for that purposes, and it can be in any field, right? So in any disciplines, we're going to use graphs to do some sort of modeling for you. So it's very, very useful. It has a lot of use in mathematics, and it has a lot of use also in the computer science. So we're not going to talk about graph theory really, and we're not going to go to those details. We just want to talk about some of the most important graph algorithms. What is the graph? So we're going to introduction to it. So of course, in the course such as data structure and algorithms, or even advanced algorithms, you're going to see a lot about graphs. So graphs are really become very, very important. So here also basically we're drawing this graph, and so as you can see, sometimes the graph can be directed. So if you connect the nodes, so those are the nodes that we have, and we have edges. So basically the graph definition can be you can say that this is it's a set of edges and nodes, right? That those nodes are going to be connected through those edges together. So that's basically the definition of it. So that's what the graph is. So the graph can when we can go from node 0 to node 3 only, and we cannot go from 3 to 0. That means that you have a particular direction in this graph. So the graph can be directed or undirected graph. And so the original I don't know why it's my video sometimes showing recently the slides a little weird, so I have to share the main. Oh, didn't get fixed. So I don't know if the problem is what my connection or what. So let's see if that helps at all. Okay, I guess it's get better. Okay, so one of the very like old modeling problem was the this basically bridge problem, and there was like two islands that people were trying to create bridges to connect the island to the basically main part of the cities. So we had like some land A, and then we have some land B, and then we have these two islands C and D, and we wanted to kind of connect them using these bridges. So the question was, did you model this kind of like a graph you see on the right side? And the question that they wanted to answer is that, is there a path starting from any vertex, traveling all edges exactly one time only, and returning to the starting vertex? So basically we start from A and we go all the way to all the nodes without traveling them again, and we come back to the traveling any of these edges again like twice, and we come back to the A again. And the answer, as you can see in this particular one, is no, because we're missing one edge basically. So that was the answer, the question. By modeling this and trying to kind of applying some algorithm, the graph, stuff like that, they were able to find out their answers and if they need an extra bridge or not. So the nodes now here are going to be those lands, and the edges are going to be the bridges that they have to make. So we already talked about the tree structure, so you can kind of have now some idea what the tree was look like, and so you can now see what is the differences between the tree and the graph. Tree and graph, they both had nodes basically, and they both had edges, but there were a lot of rules we talk about. When we talk about tree, we talk about a lot of rules that we don't have any of those rules in the graph. So tree, for example, tree is basically a special kind of graph, right? So we're only going to have one root, that's for sure, right? So we do have a root, and we're going to have one root. And also we know that if we have n nodes in the tree, we're definitely going to have n minus edges. We know that every single node, they're going to have exactly one parent, and root is the only one doesn't have any parent. And also all nodes must be reachable from the root through exactly one possible path from root to that node. So these are some very important rules about the tree. Otherwise, that's not tree anymore, right? So the tree has its own definition. It's a very special kind of graph. But graph doesn't have any rule, right? So and that makes it a little bit too flexible sometimes, and also interesting. And now we're going to talk about some basic terminology about the graph. So what is a graph? So graph is a set of vertices and edges, nodes and edges. So that's the definition of the graph. Some graphs are directed, some graphs are not. So we call it undirected graphs. So basically, if we're going from one node to another node, it has a particular direction, then we have to use a directed graph. So then edges are going to be have directions. Sometimes we have weighted graphs, and sometimes we have unweighted graphs. So that means going from one node to another using a particular edge is going to have a particular price for us, for example, or it has a weight. It can be that a weight can be the price of toll tag, it can be price of shipping cost, the price of air tickets, basically. So there can be anything, depends on what this your model is all about. that weight is going to have a specific meaning for it. And it can be also an unweighted graph. So that means all of the edges going to have exactly the same weight, or which is or no weight at all, right? So basically, there's no difference between one edge to another. So the adjacent vertices or edges are basically connected by the same edge or by the same vertices. So adjacent vertices are connecting to the same, both connected to the same edge, right? The two sides of the same edge, and then connected or adjacent edges are also going to be connected to the same vertices. So the ends of both of the edges going to end to a same node. Neighbors are vertices, or neighbors edges are going to be the two vertices or two edges that are close to each other, adjacent to each other, right? So basically I can go from one node to another node through one edge. That makes those two nodes to be their neighbors. Or I can go from one edge to another edge through one single node. That makes those two edges to be their neighbors. Whenever we have a loop inside a graph, that means that there is an edge that links a vertex to itself. So that means we have a loop, right? So we can go from one node A and come back to the node A again. So here an example of a directed graph. So as you can see, we have directions. So we can go from Jane to Mark, or Peter to Mark, but we cannot go from Mark to Peter. From Mark, we only can go to Wendy. This is some other basic terminologies, like what is a parallel edge, right? So the parallel edge are they both have they're going to from same node basically, right? So here we may have parallel edges. We'll see if we have one. No, not in the example here, but simple graph is the graph that doesn't have any loop in it. A complete graph. So we have a complete graph right here in the picture. It means we have that entire, every possible edges that we can create to connect this basically graph together. That is going to be a complete graph. So where we have a connected graph, right? So connected graph is basically connected graphs are all, with all the nodes somehow they connect to each other. So from basically one, you can go from one node to another somehow through a path, right? So it's not there is not some disconnection between the elements inside a graph. Another thing is a spanning tree. So the spanning tree is going to be created from the graph. So here in this picture, we have a graph that is completed graph here. And if we want to looking for the tree that, okay, so we already know what is a tree, right? So the tree is going to have only one starting root, and then from that, we're going to go over all of the children, and we only going to have one father per children. So we have to get rid of extra edges, that basically. But we're going to still keep this graph as connected as possible, right? So we're going to keep minimum edges as possible to go to that node, or we're going to get rid of the rest. So that's creating a spanning tree. One graph can have multiple different spanning trees, and we have an algorithm to do that. So we kind of see some of them today as well. That's going to be helping us to traverse a graph and create basically a tree out of that graph.